So now let us talk about stresses in soil mass. So this is just actually a continuation of the discussion that we had previously on stresses in soil, or actually that part have focused on the effective stresses of our soil. Alright, so construction of a foundation causes changes in the stress, usually a net increase. So the net stress increase in the soil depends on the load per unit area to which the foundation is subjected. So the depth below the foundation at which the stress estimation is desired and other factors. It is necessary to estimate the net increase of vertical stress in soil that occurs as a result of the construction of a foundation so that settlement can be calculated. So this chapter discusses the principles of estimation of vertical stress increase in soil caused by various types of loading based on the theory of elasticity. Although natural soil deposits in most cases are not fully elastic, isotropic or homogeneous materials, calculations for estimating increases in vertical stress yield fairly good results of practical work. So this topic, or this discussion, or this module rather, is just an introductory part of the stresses in soil mass giving discussion, which represents our shear stress. No? So to determine the normal stress and the shear stress on plane EF, now we have a point or a plane in consideration right here, which is EF, no? Which is siguro considered as the plane of failure. No? So to determine the normal stress and the shear stress on the plane EF that makes an angle theta with plane AB, we need to consider the free body diagram EFB shown in figure B here. So let sigma n and tau n be the normal stress and the shear stress here respectively on plane EF. So from geometry we know that EB is equal to EF cosine theta and FB is equal to EF sine theta. So summing the two components of forces that act on the element in the direction of our normal stress and the shear stress, or the N and the T axis, we have this one, or we can come up with this formula here for our normal stress and our shear stress, as well as our tangent to theta, or the computation for our theta. So these are one, or this could be the formula that you may use later on in problems related to the determination of normal stress and shear stress of a soil element. So for the given values of um, tau sub xy, or this is our shear stress, and our sigma y and sigma x, which are our normal stresses, the previous equations nakatagganiha will give two values of theta, no, that are 90 degrees apart. So this means that there are two planes that are at right angles to each other on which the shear stress is 0. So such planes are called the principal planes. The normal stresses that act on the principal planes are referred to as principal stresses. So the values of principal stresses can be found by these equations, no? Or these formula. Our major principal stress, or sigma 1, no? We can calculate that using this formula and as well as this one. Although you don't need to really memorize this formula, because later on there would be an introduction of another way to solve for these stresses. Okay, so we have the Moore's circle. Now, I know some of you are already familiar with Moore's circle, because Moore's circle is not only applicable for soil mechanics, but it is also adapted in subjects like strength of materials. So the normal stress and shear stress that act on any plane can also be determined by plotting Moore's circle as shown in this figure. So the following sign conventions are used in Moore's circles, which will later on be very useful for us in drawing our own Moore circle. So compressive normal stresses are taken as positive, and shear stresses are considered positive if they act on opposite faces of the element in such a way that they tend to produce a counterclockwise rotation. So meaning, in our Moore circle, we have to adapt the sign conventions, which says that Compressive normal stresses will have positive sign, and shear stresses that will incur counterclockwise rotation on our plane of consideration will have a positive sign. So the opposite for that will have a negative sign. So for plane ED, we have here the norm, yes, a normal stress equal to delta x, sigma, no, not delta, sigma x, and shear stress equals tau sub xy. No? So for plane AB, the normal stress equals this one, no? Sigma y, and shear stress equal to our tau sub xy. So points R and M in the Mohr circle represent the stress conditions on plane AD and AB respectively, no? So kani sila nga mga stresses, pag abot dito sa tong Mohr circle, i-plot na to na siya in points R and M, no? Kay we have our y-axis here is for the shear stress, and our x-axis will be our normal stress nga axis, no? So anything or any movement along y-axis will represent our value for shear stress, and any movement along x-axis will represent a value for our normal stress. So kaning sigma y dinhi is actually can be plotted along our normal stress or our x-axis here, as well as the tau sub xy can be plotted along our um, y-axis, no? So O is the point of intersection of the normal axis or the normal stress axis with the line RM, or that is the center of our circle. So the circle MN QRS and OR as the radius, and as the center would be Z or O, no? If this is our circle, our center would be O, our radius is equal to OR, no? Or OM either. It could also be. So the radius of the Mohr circle can be calculated using this equation. Or it could be directly plotted in the normal stress axis or the x-axis, no? This is this distance from this point of the circle or the center of the circle at point O. That is the distance from the origin, or we can use this equation. So the stress on plane EF, no, which is the point of consideration, can be determined by moving an angle equal to 2 theta, which is twice the angle that plane EF makes in a counterclockwise direction with plane AB, no, in this figure. In a counterclockwise direction from point M, no, we have to move from OM, we have to move an angle equal to 2 theta, and then we could reach the point Q rather. So the abscissa and the ordinate of point Q respectively give the normal stress and the shear stress of plane EF. No? So from point M daw, we have to move 2 theta in a counterclockwise direction, and then we will arrive with, if we are going to project that one, the point in the Mohr circle, no, given by this 2 theta from our point M or from our line OM, ang kani kunong coordinates, meaning the abscissa and the ordinate of this point Q here, will give the normal stress, which can be taken from the abscissa or the x value, and then the shear stress will be given by the ordinate of this point. So because the ordinates, that is the shear stress of points N and S, are 0, they represent the stresses on the principal planes. So the abscissa of point N is equal to sigma 1, and the abscissa for point S is sigma 3. Okay, so S in here is actually our minimum principal stress, or the nearest point or nearest distance from our origin in the Mohr circle, no? And then our point N in here is actually the maximum principal stress, or our sigma 1, which is the farthest point from our origin in the Mohr circle. So as a special case, in the planes AB and AD were major and minor principal planes, the normal stress and the shear stress on plane EF could be found by substituting this is the shear stress, or the tau sub xy equal to 0. Thus, we can come up with this equation. No? We can use this equation in order for us to solve for the normal stress in our plane EF, or the abscissa and the ordinate here. We can also use this equation. So the Mohr circle for such stress condition, no, shown in this figure, the abscissa and the ordinate of point Q give the normal stress and the shear stress respectively on point EF here. This is the plane EF. Ang iyang normal stress or shear stress ani will be given by the abscissa and the ordinate of this point Q here respectively. So we have here more on Mohr circle, so that discussion that we had no just recently um was taken from the book of Brahadas, and this explanation or this discussion here is given by a review book by Besavilla. So we have here our soil element, no, with stresses acting on it, no, the same like pagkaganiya, and this would be our Mohr circle. And then we also have, from that we also have another equations that will enable us to arrive with the value of our radius of the circle and the tangent to theta nga value, no? So same lang gyapon siya, although you don't really need to understand this, because later on we will have a sample problem which will elaborate on the parts of our Mohr circles. All you have to do is just be familiarized with the parts of it, no? We have on the Mohr circle, we have the Q1, which is the maximum principal stress. That would be equal to our sigma y plus sigma x divided by 2 plus our radius, and our sigma 3, which is our minor principal stress, which is equal to this one, or this is actually the equation for our center, no? Sigma y plus sigma x over 2 minus the radius. So, mao lang siya diri. And our tangent to theta value can be solved using this equation. So, our shear stress on plane AB in here is the plane of failure, no, would be equal to this equation, or can be computed using this equation. And the normal stress on plane AB, no, using this Mohr circle, can be calculated using this equation. And yes, you have the freedom to just memorize these equations, so that later on, using the given values of our sigma y and sigma x, and computing the value for our radius using this equation here, no, which can also be derived or taken using the given values for sigma y, sigma x, and our shear stress, no. So our 2 beta and 2 theta as well can be taken from our Mohr circle. These are these angles. So more on Mohr's circle, no, we have the pole method of finding stress along a plane, that is plane EF in this case, no. First we have to draw a we also have to plot, no, the points N and M here using the given stresses in the problem, and then from that you have to draw a line MP parallel to AB. So from point, di ba, establish ni ang N o ang M din ni pinakauna, and then you have to draw a parallel line to AB, that is a horizontal man AB, no. So you have to project that one, and then draw a line parallel to EF na dayon, and then we will arrive with your point Q, wherein kining point Q ang bisag coordinate o yang ordinate ani rather will be the normal stress and the shear stress of our plane EF respectively. So we have here example problem number one, no? So we have to solve for the magnitudes of the principal stresses and the normal stress, and as well as the shear stress on plane AB without using the Mohr circle. So we are given here our figure, and the stresses are, we have the normal stress equal to 2,000 pounds per square foot, and our shear stress is equal to 800 pounds per square foot, and our sigma y is equal to 2,500 pounds per square foot, and our theta is equal to 20. So we are asked to determine the magnitudes of the principal stresses, meaning the minor principal stress and the major principal stress, and as well as the normals and the shear stresses. So ang kaning diring mga given values, we have to plot this if we are going to use the Mohr circle. But this time, we will just stick to the equations given by the book of Bradas. So we have this solution here, no? Kani siyang equation is given already. So all you have to do is plug in all the given values, no? And then you will come up with your sigma 1, which is your major principal stress, and your sigma 3 is equal to your minor principal stress. So your principal stress therefore is equal to 3,088.15 pounds per square foot, and your sigma 3 or your minor principal stress would be equal to 1,411.85 pounds per square foot. Alright, so the next being asked are the normal stresses and the normal and the shear stresses rather. Alright, so these equations are already given. Now this equation for the normal stress and the shear stress are already given, no, based on our previous discussions. All you have to do is plug in all the given values for sigma y and sigma x. Now, by the way, this 2,000 pounds in here is actually sigma x. Your sigma y would be equal to 2,500. So computing this one, you will come up with the values of your normal stress and your shear stress respectively. So that solution is simply based on the equations, no, given by the previous discussion. So although if you are not able to memorize the equations for that, no, for the principal stresses, the normal stresses, and the shear stress, you have another option, which is the Mohr circle. So this is another sample problem, no, which we will be using the Mohr circle in order for us to compute for the major principal stress, the minor principal stress, and as well as the normal stress and the shear stress. Alright, so for the solution of the sample problem number 2, first let us compute for the major principal stress. So before we can do that, we have first to establish our Morse circle. So for us to do that, let us have first this, and then we will discuss now how did we come up with this circle. No? So first we did basically in establishing our Mohr circle, we have to establish first a point and then another point, and then we just have to connect that and then draw a circle around it, and from that that will be our Morse circle, where we would identify our major principal stress, minor principal stress, our normal stress, and the shear stress at our point or plane of failure here CE, no, kay kani siya nga problem naga-focus gid siya diri sa atong plane of failure CE. So first, let us focus on the given values, no, we have this one. So sa Mohr circle, kani siya nga mga given values, kaning first set sa ato ang shear and the normal stress, no, duha siya ka set, kani sila ang mag serve as initial points in our Mohr circle, no? So, we know nga ang the normal stress will be on or will serve as the abscissa or the x coordinate of our point, and then the shear stress will serve as the ordinate of our point, no, in the Mohr circle. So duha siya ka points kay bali kay duha man siya ka set sa coordinates, no? So first we have to recall the discussion that we had, no, on the sign convention for establishing our Mohr circle. So we have a compression will have a positive sign, and the counterclockwise direction of rotation will have a positive sign. So first, this one, no, our normal stress sub y, which is equal to 50 kPa, naa siya iyahang counter dili sa iyang opposite side, no, kay maginani magiging given. So iyang counter ani is this one, no, pasaka siya. So therefore, this will have a compressive effect on our plane CE, no, kay the direction of the force is towards man our plane CE. That's why it would tend to compress our plane CE. Therefore, it is compression, and therefore it will have a positive sign. Okay, now next, this shear stress XY, which is equal to 50 kPa, no, directed towards the left, ang iyahang counter ana is this one, no, this AB here. So therefore, it will cause a rotation like this in this direction against our plane CE, no. Therefore, if it will rotate in this direction in respect to our plane CE, it has a counterclockwise direction. Therefore, it will incur a positive direction. So that would be on the first set of our points or coordinates for our Mohr circle. So next is this one, no, these given values here. First, let us have the normal stress sub x, which is equal to 150 kPa, this one. So it is directed towards the left, and it has a counter on the other side, no, on the opposite side, which is directed towards the right as well. So therefore, it tends to compress again our point or our plane CE here, because it is, or they are both directed towards our plane CE. So therefore, this normal stress sub x is which is equal to 150 kPa, will have a positive sign because it is compression, no, in respect to our plane CE. Now, this shear stress 50 kPa, no, shear stress sub xy is directed towards the bottom, no, or downwards. Yung counter ani on the opposite side is this one, and it is directed upwards. So therefore, in respect to our plane CE, it will rotate in this direction, and that direction is clockwise. So therefore, our sign convention says that counterclockwise rotation will have a positive. So clockwise direction will have a negative sign. So this here is one set of coordinates of a point in our Mohr circle as well as this one. So therefore, kani siya, x is equal to 50, y is positive 50. So therefore, our coordinates here is 50, comma 50, or 50x, or a positive 50 for our x and positive 50 for our y. So isa na siya kaset, no, sa atong x o y coordinates, our abscissa and our coordinate. So for this second set, ang atong coordinate here would be positive 150, comma negative 50, or our abscissa is positive 150 and our ordinate is negative 100 negative 50 rather. So if we are going to point or to plot this, no, on our Mohr circle, so we have here our Cartesian plane, wherein atong y-axis will always be for the shear stress, and our x-axis will be for the normal stress. So any movement along the y-axis is our shear stress, and any movement along our x-axis will be the value of our normal stress. So first, this set of coordinates, if we are going to plot this in our Mohr circle or in our Cartesian plane, no, 50 ang x, so we are going to move 50, and then ang y is positive 50 man, so masaka sa tag positive 50. So that would be this point, no, and that is our point M. So, kaning next pod nga set sa atong coordinates, if we are going to plot this in our Cartesian plane, atong x is 150, positive 150. So, we are going to move along our x-axis, no? Kay normal stress man siya. So, we are going to move equal to 150. And then, ang atong y din ha is negative 50 man daw, no? Dire. So, from that, 100, positive 150, and then negative 50. So, that would give us this point n. No? So, ana siya. Initially, wala pa ni siyang circle, no? Na lang siya sa drawing kay para gusto lang ako siya ipakita po sa inyo, ha? Okay. So, let us focus on the colored ones, no? Kaning illustrate in the illustration. Okay. So, next, if we have these 2 points, all we have to do is connect them. This will serve as the diameter of our Mohr circle. Alright. So, if we are going to draw a circle around that, then we have our Mohr circle already for the soil element with these given stresses, no? So, therefore, our circle has a center at this point, which is the distance would be equal to 100, no? Kay 100 man ni siya diri, So, ang kanang pag-measure sa 100 is just, maragi assume lang siya, no? Or bana-bana lang siya kay, if this is 50 and this is 150 here, kaning nga point, so we can just manually, identify kung pila ang atong, distance sa atong center from the origin, no? Tama. Or, that is, 50 plus 150 divided by 2, no? So, alright, so if we have a circle, the next thing that we have to do is identify its radius. And for us to do that, let us consider this triangle, no? So, kani siya nga triangle, iyang dimension ani is, so this bottom part of the triangle would be equal to 100 man daw ning center, tapos na rin take abscissa diri nga equal to 50, no? So that is 100 minus 50, so 50 ni siya diri ang sukod aning bottom part sa tong triangle. So ang kanida yung vertical part sa tong triangle would be equal to 50, no? Kay ang kani siya nga movement dani sa atong along our y-axis is actually equal to 50 kPa. So our triangle therefore is 50 by 50 ang iyang vertical o horizontal nga dimension. So if we are going to solve for that, meaning this is a right angle, meaning we can use the Pythagorean theorem. So r squared is equal to 50 squared plus 50 squared. So our radius for this Mohr circle would be equal to 70.7. Okay. So the next one, we are asked to compute for the major principal stress. Actually, ang kanang major principal stress, mao na siya ang maximum normal stress sa ato ang Mohr circle. No? Kay our principal stress is the normal stress man. So, meaning, ang pinakadako, no, nga principal stress nga ma-experience sa atong soil particle or soil element is actually the farthest point, no, from our origin in the Mohr circle. So, meaning, that is this part here. Butang nato diri siya nga part, no? It is the farthest point from the origin in our Mohr circle. So that is, if our center is 100 away from our origin, meaning this point here is 100 plus the radius. So that would be 100 plus r, which is equal to 70.7. Therefore, our major principal stress is equal to 170.7 kPa. Or you can also use the formula that we have previously discussed in the previous slides. So now, the next is the minor principal stress. So ang minor principal stress is the nearest point from the origin in the Mohr circle. So, mo ni siya, no? This is the origin. Ang iyang pinakaduol nga point sa Mohr circle is this one, no? or that is 100. If this is 100, no, our center, minusan nato siya r, mo ni siya nga distance, or our q3, or our sigma rather, our sigma minimum, which is our minor principal stress, and that would be equal to 100, or the center, minus the radius, that would be equal to 29.3 kPa. So that is our minor principal stress and our major principal stress. Although you can also use the formula for this one that we have previously discussed. Okay, so the next thing that we are asked for is the normal stress and the shear stress, no, on point CE, or on our point of failure or plane of failure CE. So for us to do that, we have to follow these two steps, no, or most common steps, although there are a lot of ways on how to proceed with the computation of our normal stress and our shear stress for point CE, no, but let's just follow this one. First, we have to draw from point M, draw a line NP parallel to line AC. So from point N daw, we have to draw our line parallel to AC. So that is vertical line. So we have to draw a vertical line. So that is, and I don't know if you were able to see that, that is the yellow line, no, projected upwards. The second one, so that would be our point P, no, that is parallel. So line NP in here is parallel to our line AC, no. So the next one is from point P daw, draw a line PQ parallel to CE. So, matong CE, no, it has a 12-degree angle from the vertical. So, we just have to reflect that, or this scenario, into our Mohr circle. So, to do that, we are going to project a line PQ, no, with a angle from the vertical equal to 12 degrees. So, man siya kibali ang atong line CE, or our plane CE, which is our plane of failure, no, ang kaning PQ. So, therefore, kaning point Q, ang iyahang X value in here would be the normal stress, and then iyang Y value here, no? Kay syempre, Cartesian plane man na siya, no? So, every point in here along the x-axis is actually the normal stress, and any point along the y-axis will be our shear stress. So, meaning, kaning point Q din ni, similar siya sa atong point point E diri, or atong line PQ represents our line CE in here. So, basically, the coordinates for our point Q will be our normal stress and the shear stress for our soil element here. And then, before we proceed, naatay gi principle na gina-follow si Mohr circle, no? It is ang movement daw din ni, we have to do a movement, no, along our Mohr circle equal to 2 theta. Kung 12 ni siya diri, we have to move 2 times the theta, or that is 24 degrees along our Mohr circle. So mo ni siya kibali, no? So, kung 12 na, we have to move a 24 degree, or we have to move for 24 degrees ani, no? So, from here, we have to move 24 degrees, and that would be on point Q as well, and the theta from between them would be equal to 2 theta, or that is 24 degrees, no? So, given ni siya always ni siya ginabuhat when we are doing Mohr circle. So, to focus on this area in the Mohr circle here, so we can arrive with our normal stress and the shear stress for the soil element, let us isolate that one. So, muna siya, no? We have our point Q, no? Para kaganiha. And then our point N, magpunta siya kaganihan, our radius. So, di ba, ingon si Mohr circle, nga mag-move daw ka og 2 theta, no? From this towards our point of focus, kay bali mo ni siya nga atong point of, or plane of failure, no? Yang theta daw ana is 2 theta, or in this case, that would be equal to 24, no? So, kung kani siya 45, no, based sa atong similar triangle kaganiha din ninong atong gibuhat. So where we have arrived the value of our radius, no? 45 man to diri ano. So based on the solution, so meaning kani pud siya diri 45 pud ni. So kung kana siya 24, meaning ang kana diyang nabilin is 21, no? So meaning ang atong coordinate or no, the abscissa for our point Q in here is 100 plus this here, this distance, no? This one. Let me show. So, ang inyahang, we know that the normal stress is actually the x, no? Is the distance from the origin along the x-axis. So, meaning, iyahang distance ani is, would be equal to 100, sorry, let me redo that one. It is 100 plus this distance, no? Muna siya ang atong abscissa for this point Q here. So, I hope nasabtan siya diya nga part, no? So, now, all we have to do is solve for this area. Solve for this distance. Okay? So, if we are going to consider, and for us to do that, we have to consider this triangle. So, kana siya nga triangle, no? So, ang kani would be equal since this one is actually the radius. So, and we have a known angle here, meaning that is r cosine theta, no? So, this one is equal to r cosine theta. So, therefore, our abscissa for this point Q, which represents our point of failure, CE here, is equal to 100 plus r cosine 21, no? So, and we have already solved for our radius, kaganihan, no? All we have to do is substitute that one, and we'll come up with our normal stress on plane CE, which is equal to 166 kPa. Okay. So, the last one being asked is the shear stress on plane CE. So, ang shear stress is just the y, no, or the ordinate of our point Q here, no? So, meaning this one. No, it is the distance from the x-axis na mo natong ordinate, or a movement along the y-axis. Or, in here, this is our shear stress man, diba? And our normal stress nga axis. So, any movement along here is our shear stress. So, in this case, for us to be able to get the distance, this one, no, kaning gamay, let us consider this triangle again. So, if this is radius, which we have previously solved, and then we have a known angle here, which is equal to 21, no? Therefore, this distance or the dimension of this would be equal to r sine 21, no? Kay opposite man siya sa atong angle. So, that would be equal to r sine 21, or our radius is equal to 70.7, which we have previously solved, times sine 21. Then we have 25.34 kPa, and we included a negative sign in here because it is on the bottom part of our origin, no? If this is our origin, so all the values in here will be negative. So since along y-axis, our point of consideration is in here, so that's why its ordinate will have a negative sign. Alright, so that would be all for the stresses in soil mass. Thank you so much.